So here we'll discuss the Banach fixed point theorem in continuation with our ongoing discussion on existence and uniqueness of solutions for autonomous systems. Okay, Banach fixed point theorem is also known as the contraction mapping theorem. So before we go into the theorem, we'll first see what exactly contraction map or contractive map mean. Okay, so let X be a normed vector space. Map P that takes a vector from X and gives you a vector in the same vector space X. This map P is said to be contractive. Okay, so P is a contraction map on X if there exists a rho or a positive finite positive constant rho less than 1. So rho is a finite positive constant in the interval 0 to any value within the interval 0 to 1, but not 0 and not 1. Okay, such that the norm of px1 minus px2 is less than equal to the norm of x1 minus x2. Okay, so multiplied by a rho, where and this inequality should hold for all possible pairs of x1 x2 from the vector space X. So what this is trying to say is, suppose you take a vector X, vector x1 and another vector x2. You take the difference between those two vectors and take a norm of it. Now the norm in some sense gives you an idea about distance. Okay, so x1, the norm of x1 minus x2 essentially is trying to indicate the distance between x1 and x2. Now px1 and px2 are the resulting vectors after the operation of p on x1 and x2. Okay, after x1 and x2 are mapped to their corresponding points under the action of under the map p. Okay, so now once x1 and x2 have been mapped to some vectors px1 and px2, now what you do is you take the norm of px1 minus px2. So basically you now try to look into the distance between px1 and px2. Okay, so if P is a contraction map, then what you will observe is the distance between px1 and px2 is going to be less than the distance between x1 and x2. So what essentially has happened is, after under the operation of P, the new vectors that were generated from x1 and x2 are closer as compared to the vectors x1 and x2 themselves. So essentially, under the action of P, as new vectors are generated, the distance between the new vectors will also reduce. Okay. Now this is not just for one pair of x1 or x2 or two pairs of x1 or x2 and so on. It is for all pairs of x1 and x2 that you can form in the vector space X. This condition should hold. In such a case, it can be established that P is a contraction mapping. Okay, on the vector space X. So it one can also state in the following way. I mean, the map P is a contraction on the vector space X. Okay. In case X is a complete vector space, then the norm used in the definition of the contraction mapping is the norm under which the completeness of the vector space X holds. Okay. The norm used here in this definition is the norm over which X is a complete vector space. So complete vector space means it's a Banach space. Okay, so this is what is the definition of um, contraction mapping. Okay, now with this notion, we'll move ahead and see what exactly does the Banach fixed point theorem or the contraction mapping theorem states. So let X be a Banach space, which means X is a non-vector space which is complete. So all Cauchy sequences in X are essentially convergent. Now let S be a closed subset of X. Okay. Suppose T is a map from S to S. So takes a vector in the closed subset S and gives you a vector in the subset S itself. Okay. And suppose this map is contractive on S. Okay, T is a map defined in the subset S and it is contractive on S. So we have seen what contraction essentially means. So under these conditions, that X is a Banach space, S is a closed subset, and there is a contractive mapping present um, with respect to the subset S, then there exists a unique fixed point X star in S. So there is one and only one fixed point corresponding to this contractive mapping on S. Number two, this fixed point, okay, X star, it can be found by successively operating T on any X naught in S. Okay. So under this contraction mapping, you have one and only one fixed point in the set S. And if you want to find out what that fixed point is, then this fixed point can be obtained by starting from any point in X, let's say it is X naught, and then you keep on operating T on that point. So as you keep on operating T, you will keep on generating the sequence, and as the sequence proceeds, you will see that it converges to X star. Okay, so let's dissect this entire theorem and see what are there that is given to us. Now, as I said, X is a Banach space, which essentially indicates that it's a normed vector space, it's a complete vector space. Okay, so there is a valid norm that holds on this vector space. All Cauchy sequences are convergent. All Cauchy sequences that you'll have in this vector space, they are all convergent. Okay, now we also have that X star is a unique fixed point in S. So this essentially indicates that if you take a point X in S, okay, and if T acting on X gives you back x, then this is possible if and only if x is nothing but x star itself. Okay, this indicates that it's the only uh, fixed point in the set S. Now the second statement that has been made is x star can be found by successively operating t on any x naught in S. Okay, so this essentially means that start from any vector x naught, start from any vector. So the initial vector we are denoting as x naught. So what you do is, or rather, instead of x naught, let us denote it as x1, because it's the first entry in the sequence is denoted by x1. So if I said x naught, that it's essentially x1. Okay, so the first entry in the sequence would be x1. So generate the second vector, which is tx1, then generate the third vector, which is essentially tx2. So this is nothing but t operating on tx1. Similarly, you keep on generating these vectors, which is nothing but t so basically you have k minus 1 operations, and as the sequence approaches infinity, you will see that xk will converge to the fixed point x star. So x1 is any point in S. It's not just one particular point on which where you can start. You start from any point in S, this will hold. Okay, so this is what the theorem is essentially trying to say. Now please note that in this theorem, what is given to us is that X is a Banach space, S is a closed subset, and T is a map, contractive map on the subset S that has been given to us. So to note down what is given, X is a Banach space, S is a subset of X is a closed set, so it's a closed subset of X, T is a contraction on S, which essentially means that, which essentially indicates that there exists a row less than 1, such that norm of tx1 minus tx2 is less than equal to x1 minus x2. Okay, so this is what is given to us. Now we'll see the proof of this Banach fixed point theorem, and this proof we'll see it in 5 parts. Okay, that will make it easy to follow the proof. The first part will basically try to establish that xk plus 1 and minus xk can be related to x2 minus 1, which are the first two entries in the sequence. Okay, second part will try to prove that the sequence xk is Cauchy, which means we'll try to show that if we are given with any epsilon, then we will be able to find the index number capital N, so that after that index number, whatever entry is taken in the sequence, the distance between them will be less than epsilon. So please recall the definition of what a Cauchy sequence is. Now, if and this will utilize the first the inequality that we get in part 1. Okay, now if we get it to be a Cauchy sequence, then essentially X being a Banach space, what will end up is all Cauchy sequences are going to be convergent. Okay, that is what exactly part 3 is going to be, that xk will approach fixed point x star as k approaches infinity. Okay, where x star is a point that belongs to S. Now, once we show that the sequence converges to a fixed to x star, okay, that is what we'll show. Next, we'll show that so xk converges to x star as k approaches infinity. Next, we'll show x star is a fixed point in S. That is t of x star is nothing but x star. So this will immediately follow from part 3, and then the last part will be to show that x star is unique. So we'll first establish inequality, then we'll use that inequality to establish that xk is Cauchy. In part 3, because xk is Cauchy, all and we are having a Cauchy sequence in a Banach space, so the sequence is going to be convergent, which essentially means that xk will converge to x star as k approaches infinity, and this x star will belong to the subset S. Then we'll show that this x star indeed is a fixed point in S, and finally we'll show that the fixed point that we have got in S is unique, thus establishing the Banach fixed point theorem. Okay, so we'll go through all these parts now. So each part, as we'll proceed, you'll see that is basically dependent on the previous part that we solved, except for part 1, which utilizes the fact that the map is a contractive mapping. Okay, so part 1, what we'll try to prove, that norm of xk plus 1 minus xk is less than equal to rho norm of x2 minus x1. What is the first thing? So norm of xk plus 1 minus norm of xk is less than equal to, so I can write it as norm of t xk minus t xk minus 1, and because t is contractive mapping, I can write that this is equal to rho times norm of xk minus norm of xk minus 1. So if I keep on doing this, what I end up with is sorry, this is rho to the power k minus 1. Let me see in the previous part what the previous part was correct. This is what we end up with. Okay, so just keep on doing this sequence till you reach norm of x2 minus x1. This is what we get. That establishes part 1. Now comes part 2. The sequence xk is Cauchy. Okay, so which means we have to show that for any given epsilon greater than 0, there exists n of epsilon such that norm of xm minus xn is less than epsilon for all mn greater than n. This is what we have to prove. So given epsilon, we should be able to show that I can find one such n so that this inequality holds. Okay, so so this sequence that we are talking of is being generated such that xk plus 1 is nothing but action of t on xk, where xk belongs to s, is what it is. Okay, now let m be greater than n, okay, without any loss of generality, of course, and n here is a positive index. So I can write m as some n plus r, where r is greater than 0. Okay, these are integers because they are indices. Okay, so this means what? This means that xm minus xn is something that I can write as x n plus r minus xn, right? And by using the property, triangle inequality property of norm, I can write this as xn plus r minus xn plus r minus 1 norm. So this should be less than equal to this, xn plus r minus 1 minus xn plus r minus 2 norm, and we keep on doing this till we have xn plus 1 minus xn norm. Okay, this is what we get from the triangle inequality. Now if we use the result in part 1, what we get is this entire thing can be expressed as rho of n plus r minus 2 plus rho of n plus r minus 3 and so on till rho of n minus 1 norm of x2 minus x1. So this is where we use the part 1. Now this is again going to be less than equal to, if I take rho n minus 1 common, what I get is rho r minus 1 plus rho r minus 2 till 1. This is equality here. And this is less than equal to I equal to 0 to infinity rho to the power I norm of x2, because I'm just adding positive quantities, so it has to be less than equal to this. Now rho is less than 1 and this is an infinite sum, so what I get is that this is essentially a rho to the power n 1 by rho 1 minus rho norm of x2 minus x1. Okay, so this is what we have. Now for any arbitrary epsilon greater than 0, okay, since rho is basically a number between 0 to 1, we can always find a n such that rho to the power capital N is less than epsilon times rho times 1 minus rho divided by norm of x2 minus x1. Okay, why? Because if the right hand side is more than if the epsilon is such that the right hand side is more than 1, then any value of capital N would do, because rho is less than 1. If the right hand side is less than 1, then you can always find a capital N so that rho power n is less than 1. Okay, so that is why we can always find a n so that this relationship is satisfied. Okay, also for n greater than capital N, we have rho power n to be less than rho power capital N, again because rho is uh, less than 1, greater than 0 but less than 1. Okay, so what happens is, so for any given epsilon greater than 0, since I can find this n, what I can have is xm minus xn. We have already shown that this is going to be less than 1 by rho 1 minus rho norm of x2 minus x1. This will be further less than rho to the power n 1 by rho 1 minus rho norm of x2 minus x1, and this will be less than epsilon. This is true when for all m and n greater than the n that you have just found out. So I was given with a epsilon, any arbitrary epsilon, and I am saying that I can find a n so that norm of xm minus xn is going to be less than that epsilon. So this implies the second part, that the sequence that we are considering is Cauchy. This brings us to the third part. Part 3. What does part 3 say? That xk converges to x star as k approaches infinity and x star belongs to S. Okay. Now what we have is, from part 2, xk is a convergent Cauchy. From part 2, xk is a Cauchy sequence. The sequence of xk is a Cauchy sequence, and since x is a the capital X is a Banach space, the sequence that we have is convergent. Hence xk will approach some x star as k approaches infinity. Okay, now we have to see whether this x star that you have belongs to S or not. Okay, so assume that x star does not belong to S. Assume that. Assume uh, x star doesn't belong to S. If x star does not belong to S and the sequence is convergent, that means what? Then there exists some m which is less than infinity, such that xm belongs to S, but xm plus 1, which is generated by action of t on xm, does not belong to S. Okay, but what we know from the definition of t is, but t maps vectors in S to S. So xm plus 1 has to belong to S. So we have a contradiction. Okay, therefore x star will be in S. Okay, so we have established now that xk will converge to x star and x star will be in S as k approaches infinity. Now the third part is done. So we will go to the fourth part, where we have to prove that x star is a fixed point in S. Okay, so to prove fixed point, we should be able to show that Tx star is nothing but x star itself. So let's see that x star is nothing but so let's say x star minus Tx star norm is nothing but this, and this is going to be less than equal to x star minus xk plus xk minus Tx star. And this is further going to be less than equal to x star minus xk plus rho xk minus 1 minus x star, because xk is nothing but t of xk minus 1. Okay, now from part 3, as k approaches infinity, xk approaches x star, and so does xk minus 1. So what we have is, if the right hand side is, if the k is arbitrarily large, so if k is arbitrarily large, RHS of the inequality will be arbitrarily small. Okay, so this essentially indicates that the norm of x star minus tx star can only be 0, which further says that t acting on x star gives you back x star, which means x star is a fixed point. Now once we have established that x star is a fixed point, the last part that remains is to show that x star is unique. So here, assume that instead of one fixed point, there are more than one fixed point. So x star is not unique. Assume that x star in S and there is another fixed point, let's say y star, are two fixed points such that x star and y star are not the same. Also, because x star and y star are fixed points, x star is nothing but tx star and y star is nothing but ty star. Now using this, what we have is x star minus y star to be equal to t x star minus ty star. So norm of x star minus y star is something that can be written as t x star minus ty star. Now because t is a contraction map, this will have to satisfy the inequality, which is this. Now since rho is less than 1, what we are seeing is norm of x star minus y star should be less than equal to should be less than the norm of x star minus y star itself. So this inequality will hold only if x star is equal to y star. So since rho is less than 1, so it is between 0 to 1, this inequality holds. The inequality holds if x star is equal to y star, that is the norm of x star minus y star is 0. Okay, now since apart from x star, the other fixed point that we had chosen was a randomly chosen point y star, and we ended up showing that x star is equal to y star. So then this indicates that, I mean, this is only possible when this, so our assumption is contradicted. Our assumption is contradicted. So x star is a unique fixed point in S. Okay, now as far as the second statement goes, that x star can be found by successive operation on any point, successive operation of t on any point in S, that actually follows from these parts of the proof. So if you notice, when we said x1 and then we used xk plus 1, so that x1 was just any arbitrary point that you can choose, and what we ended up showing that x star is a unique fixed point in S. Okay, so that also establishes the second part of the Banach fixed point theorem. So hence this completes the proof for Banach fixed point theorem. In the follow-up lecture, what we'll see is how this will be used to establish uniqueness and existence of a solution for a autonomous system. So we'll stop here. Thank you.